Right, exactly. So that's given. So if we remember for saturation, the requirement is that VDS has to be greater than or equal to overdrive voltage. And what is overdrive voltage? We know that's the gate to source minus VTN. So, which means this guy is definitely have to be subtracted threshold voltage from this, which means this is going to be smaller than this guy, right? Do you follow this? Right, so if these two are equal, it definitely means VDS is going to be larger because VGS is, we will have to subtract threshold voltage from it, and then we'll get to overdrive voltage. So thus overdrive voltage will be smaller than VDS. Follow me or not? All right, give me some feedback. So I know if I need to repeat that, go over this. So that means this satisfies and that's saturation, right? So table 5.1, page 263, we will apply the equations that are given under saturation region. Now, in this situation, we are given the drain current and we are given these values. And we don't know the Kn parameter and threshold voltage. How do we go about it? So two equations. Okay. So equation of drain current, if I write it in saturation, is half Kn prime W over L VOV squared. And VOV, I can expand it to this guy. So we have this equation, and we are given two situations for this equation. So we have two equations and two unknowns, right? Two equations and two unknowns. So what do? Just plug in these two situations with one with this drain current and one with this drain current. So we'll have two equations. We play with this and we calculate the unknowns, right? So first situation is ID is half Kn. So this we can write together, Kn times VGS minus VT whole squared. So in this equation, I need to plug in those two values. So let's plug in the first one, which would make it 0.36 equal half Kn 1 minus Vt whole squared, right? That's 360 amps at this VGS. That's equation one, let's call it one. And I plug in the second situation. Yeah, go ahead, Nestor.
The 0.36, it went from micro to milli, right? You're using milliamps now?
No, we are using amps. So milliamps, sorry. Yeah, we're using milliamps. So we bring that to the same. And now we plug in the second value for 0.8 volt. The current is 0.16 milliamp, unknown 0.8 minus Vt squared. We just have to solve these two equations. Do unknowns, two variables. So let's call it equation 2. Right. So divide 1 by 2 or 2 by 1, whichever we want to do. And taking square roots, this gets simplified as 1 minus Vt over 0.8 minus VT, right? So you play with this, so we get threshold voltage as 0.4 volt. That's one part. Now, you can plug it in one, or you can plug it in two, and you will find Kn, right? So just plug it in equation one, and that would make that 0.36 equals half Kn times 0.6 squared, and that will get you Kn of 2 milliamp. So yeah, so Kn is in milliamp, and that gets you both of these values that we need. So the first step to identify what is the mode of operation and how do we go about using that relationship that is specific for that operation region. All right, let's look at another question, 5.19. So here we are given transconductance parameter, Kn prime, given threshold voltage. Again, we are given this situation where VDS is equal to VGS. What mode of operation is this transistor in?
Saturation.
All right, very good. And same argument applies like we saw before, that for saturation, this needs to be satisfied. If VDS and VGS are equal, then which means overdrive voltage is going to be smaller than VDS, because threshold voltage needs to be subtracted from VGS. So being equal tells us right away that it is in saturation. So we'll use saturation equation for that. Now we are given drain current and we are given length. We are not given width. Can somebody help me write this equation now?
It would be ID equals 1/2 Kn prime times W over L. And then VOV squared.
VOV, let's expand it.
VGS minus VT squared.
Squared, very good. Let's now plug in the values for me. So
it would be where VGS minus VT, it would be 1.8 minus 0.5.
yeah, so let's start with drain current. So what's the equation? 2 equals half
Of 400, or excuse me, that one would be in milliamps, correct?
milliamps. Yeah,
So then 0.04.
0.04, very good.
Oh, no. Point. Yes, sorry, I'm
Oh,
confused.
sorry, 0.4. Yeah,
0.4, yes, okay.
thousand. Yeah, 0.4. All right,
Times W over that one would be, would it be 0.18, or do we also have to change it to milli?
Yeah, so we have to match the units. Yep.
So then it would be 0.00018.
So you have to remember W over L is a ratio of lengths, so it doesn't matter. But
Okay.
whatever we use here, then the other thing will be in the same units,
Okay,
because
so
the
then
units gonna cancel out. So
just the 0.18.
let's keep it like this. So when we solve, then it will be easy. We can just plug in this 0.18 at the end. All right, and
And then
VGS
1.8
1.8,
minus 0.5
0.5 squared,
square.
right? So now when you get everything settled, we get 5.92. And here now, then I can get the length. So W would be then 5.92 times. So if I'm using micrometers as is, the width would be in micrometers. So straightforward, just some straight multiplication. All right. So let's look at another question. A little bit. Yeah, don't get scared from the too many lines. If you look at it, it's just asking things in succession, and we just follow again what is the mode of operation and what is the how we have applied this. So here they have said it's a linear resistance region. So linear resistance region is the triode region. So let's go to the table 5.1. So, okay, we see what is triode region and what is the drain current equation for that. All right. So it's conducting 50 microamp for this gate source voltage, and then this much drain current for this much drain to source voltage. So again, two situations have been given. It gives me idea that maybe there are two missing variables that need to be found out. Okay, we'll see. What's the apparent value of threshold voltage, VT? We just did that, right? So we can find out. If Kn prime is this much, what's the width over length ratio? We just did that as well, right? What current would you expect to flow with? Okay, now it wants us to change the gate to source voltage. The two situations were given. Now it wants us to apply another situation and says, okay, VDS is this much. Now here we can see VDS is smaller than VGS. Of course, it's given that it is linear region. So it's in triode region, of course. So it's not saturation. So hence we can see that. Now then it says if VGS is operated this much, what value of drain source rates will the drain end of MOSFET just reach pinch off? And when does the pinch off start? When VDS is what value? So that's again table 5.1. When do we get to pinch off? What's the time when the pinch off starts?
When it starts to get in saturation, or?
Exactly, that's the start of saturation. So what's the condition for saturation? What two voltages have to do what for the saturation start?
VDS is greater than or equal to 0.
That's
voltage.
the saturation region, but the start of saturation is?
They equal to each other.
VDS will be equal
to the override voltage.
Override voltage, right? So that's the start. And of course, then the region is that it has to be greater. But the start is when it's just equal, and that's the onset. Okay, we'll get to that. And then what is the corresponding voltage at the drain current? So when we'll find out the VDS minimum, the minimum value of VDS, which is the minimum value of the drain of the saturation region, then we'll use the saturation relation to find the drain current. All right, let's see how do we break it down now. So first thing, so this is the table 5.1. So who's gonna help me identify what equation to use here for the drain current? For the drain current.
Would be half Kn prime W over L and override voltage squared.
So we have Kn, right? VOV times VDS at just the onset. So VOV is VGS minus VT. That's the linear resistance region. You have to, if you look at the figure, it's the early part of the triode region. So let's plug in the two situations that are given. One is given for 50 microamp and the other is for 100 microamp. 0.8 minus VT times 0.05. And the other situation is 100, 1.2 minus threshold voltage times 0.05. So again, two equations, two unknowns, divide 1 by 2, we get, let's divide 2 by 1, that's going to make our life easy. 100 divided by 50 is 1.2 minus VT divided by 0.8 minus threshold voltage. So we find threshold voltage 0.4 volt. And you plug in into any of these, we get the Kn value from that. So we plug into the first one, 50 is equal to Kn times 0.4 times 0.05. Right? That was 0.8 minus VT. So get this guy, it's 2.5 milliamp. So we were doing microamps here, but now we will convert it to, we can convert it to milliamps at the end. These we were using microamps as it is. We could have converted them here, but we will convert, this answer will be in microamps, so we'll convert it into milliamp. Let me just take that step so we know we didn't skip anything. So Kn would be 2500 microamp per volt square, which is 2.5 milliamp per volt square. All right, so now that's the VT. But now it didn't ask us for Kn, but for width to length ratio, we need to find that, right? For that, it's given us Kn prime value, which is different than what we found here. So Kn prime is 500 microamp per volt square. That's given. So width over length ratio from this would be 5. So if we remember, this was Kn prime times this guy. So we just plugged it in here. So they have 2500 divided by 500 gives us the ratio of width and length, right? So that's what was asked about that. The third thing that was asked, what current would you expect to flow with this VGS and this VDS? Right, so let's plug in that there. VGS is 1 volt and VDS is 0.2 volt. So now we have to use that expanded version of the drain current, where we specifically take in the gate to source voltage and drain to source voltage. That's table 5.1 should be Kn times VGS.
VGS minus VT.
VT times VDS
Yes.
minus half VDS squared, right? So again, straightforward plug and play. You know this guy, this. So I'm just gonna skip to the answer to get 0.25 milliamp, or you can write it in microamp, just move it 3 spaces to the right. Now pinch off says if VGS is this guy, when does the pinch off occur? So that would be VDS is equal to VOV, right? So that's the VDS at the onset when it starts has to be equal to VOV, right? And VOV means it has to be VGS minus threshold voltage. So we are given this guy and we know threshold voltage. So just plug in the values and that gets you 1 minus 0.4, which is 0.6 volt. So that would be the onset of pinch off. Now the last part is, again, just using the saturation current equation, which we have done in previous questions. So what value will drain and just pinch off, and what's the drain current? So straightforward, same way, just plug in this equation to find the drain current in the next question, right? So I'm gonna skip the last part where all we have to do is just use that 5.1 last equation to find drain current, where we know Kn, where we know gate to source voltage, where we know threshold voltage, and we know VOV. So just plug in there and we get the drain current. All right. Let's look at another simple problem. So I hope it's becoming simpler now, right? All right. So NMOS threshold is given, operating with gate to source in the range of 1 to 1.8. What's the largest value of drain to source for which the channel remain continuous, right? So when you say continuous, what does that mean? So we have to be in the triode region. So we are talking about this region. So it's a continuous equation. It's a linear relationship. So what we have to do is just write for this situation, VDS has to be smaller than equal to VOV. But we can write down VGS minus VT. So if this range of this is given, just plug in and we'll get the range for this guy. So VGS is from 1 to 1.8 volt. So VDS is then 1, starting from 1. VT is given, goes to 1.8 minus 0.5. So that's the range for VDS. So it starts with 0.5. Goes till 1.3. So that would be the range for VDS from the range for VGS. So what's the largest value for VDS? We have to know that this is above this value. This is going to go bigger than this is the starting where it's going to be continuous. So this is where the VDS starts. So that's the starting point for VDS. All right. So let's look at another play on the same equation. I'll just give you hints on this. What we are doing here is we have two NMOS and it says they are matched, except there is a mismatch of width over length ratio by 2%, which means in drain current equation for Q1, let me just write 1, and between ID2, you have to find this and this. And if you use 1 for W over length ratio for one case, you'll have to use 1.02 for the other case because there's 2% mismatch between those two. Does it make sense? So which means the drain currents would change because of these two things are different. Otherwise, they are matched. Otherwise, everything else is the same. So here then we are given the gate voltage is given, right? So the ratio of ID1 over divided by ratio of ID2 would be then 1.02. So that's first part, that when you calculate the mismatch in the drain current, you will see would translate into 1.02 difference between those two. And the second question, in a similar way, is talking about threshold voltage. So you have to include the mismatch of 10 millivolt. So if you have threshold voltage of 0.5 volts, then 10 millivolt would be 0.01. So one transistor would have VT1 would be 0.5 volt, and the other one would be 0.5 plus that amount, and that would become 0.51. So now again, when you'll calculate ID1 and ID2, you will have to use the threshold voltages for them. And that would then, when we compare ID1 and ID2, we will then find out what is the resulting mismatch in the drain current, right? So plug in the values, then just compare them or divide them. That would give us how far off these two go from each other. So just to get a feel of designing and a circuit where if there is a mismatch between transistors, then how would their drain currents differ because of those mismatches? Right? So you should be able to see what is the situation given from the question and what should be the equation that should be applicable for that case. So don't get confused by how the question is presented. If you identify the region, operational region, identify the parameters, you should be able to plug and play.